Hello and welcome to this lecture on chemical process modeling and simulation. Over the past couple of lectures, we have been developing a systematic introduction to conservation in transported quantities, and we have gotten an introduction to the sort of conservation equations that are written in modeling chemical systems. And then we spent one lecture on understanding how a flowing fluid, how a fluid in principle, whether flowing or not, right? A fluid is modeled at least three different length scales: molecular length scale, microscopic length scale, and macroscopic length scale. And then we were given an introduction to the fundamental continuum hypothesis, which sort of forms the foundation for modeling a fluid in microscopic and macroscopic length scales. Now, based on this continuum model of a fluid, where we do not look at molecular structure of the fluid, we do not consider how there are discrete molecules that are present, and therefore that could their movement and their interactions could cause fluctuations in the sort of intermolecular interactions, and thereby the various properties that arise out of these interactions. And then we acknowledge, however, that the properties of the fluid have molecular origins, but yet they can be assigned as some parameters whose magnitude exists. I can take, for example, the density of a fluid to be fixed in my entire volume, or if at all it varies, it has a continuous variation in space and time, right? So this kind of a model, using this model, now over a series of lectures starting from this one, we are going to gain a very good introduction into molecular momentum transport, which is not the bulk momentum transport, right? This is molecular momentum transport, and the transport mechanism that arises in this particular situation, which is one of friction, and the property of a fluid that captures the extent of this friction, called viscosity. All these we are going to sort of try to get a good understanding in this and a series of lectures. And to sort of motivate how molecular momentum transport occurs, we start with two examples. This example is going to be an example of flow between two parallel plates. Now consider, before we go into flow between two parallel plates, how momentum transport happens in rigid bodies, in solids, right? And then a car moves, or a person runs, or a bicycle moves. So these kind of momentum transport is something that you have studied in your school days, and they are all governed by Newton's laws of motion. In Newton's first law of motion essentially says that in an inertial frame of reference, all bodies will continue to be at rest or uniform motion unless acted on by a second external force. Newton's second law of motion says in an inertial frame of reference, the net force acting on the body will result in what will be the consequence of that external force that acts on the body. It will result in an acceleration that is proportional to the net force, and is related to that acceleration by this sigma f, which is the net force, is m, mass of the body, into a, which is the acceleration, and mass of the body is assumed to be constant. And Newton's third law of motion says, when a first body exerts a force on a second body, the second body will simultaneously exert a force on the first body, and that will be of equal magnitude and opposite sign. So these taken together are Newton's laws of motion, and these govern momentum transport or motion in rigid bodies. So is there molecular momentum transport in rigid bodies other than the bulk motion? So there is a car that is going, being driven, or or a ball that is rolling, or ball that is thrown up and then it goes up against gravity and falls down, there is projectile motion, for example. Is there molecular momentum transport in all these rigid bodies? Yes, and that is friction. How is friction modeled in rigid bodies? So there are two types. One is a static friction when the body is not under motion, and then there is dynamic friction when there is the body is under motion. And of course, we are interested in dynamic friction. We are looking at transport. This frictional force is proportional to the relative velocity between the rigid body and the friction causing surface. And the proportionality constant is called the coefficient of dynamic friction. If you were to look at a molecular picture of this momentum, this friction, basically what is happening is that if you were to zoom in, right, there is some sort of one substance that is moving, and then there is a substrate, underlying substrate at the bottom, purple colored substrate, and this basically results in there are atomic and molecular interactions at the interface between the rigid body which is moving and the substrate, and at that interface there is definitely formation and breaking of secondary bonds, and this essentially continuous formation and breaking of secondary bonds results in some sort of a friction, and there is some loss of energy and loss of momentum that happens through this, of course, which is why we fill fuel to propel our automobile vehicles, right? Otherwise there would be no need. Initially you give a push to a car and the car will keep on going, right? That of course is not true, because there is friction, and that the initial momentum that you impart to the car is lost to the surface, which is the road, and then the car comes to a stop unless I can continuously keep supplying momentum, right, to the four tires, the four wheels, so to speak, which will keep the car running, right? So this is how we understand molecular momentum transport or friction in rigid. Now let us come to laminar flow. This is one type of fluid flow, and we are going to look at flow between two parallel plates. Consider the flow of fluid into, say, a region between two parallel plates that are 2b, a distance 2b apart, and look at where the coordinate system is placed. The center line between the two plates is where at the entrance is where the origin is placed, and the direction of fluid flow is the x-axis. The direction of that sort of separates the two plates, that is the y-axis, and the third direction is the z-axis, and that gives the width of each plates, and it is assumed that the plates are infinitely wide and they are perfectly parallel to each other. Essentially the width is much larger than 2b. That is the idea. And initially, there may be fluid that is coming from some outer region, and say there is some distance h apart, and then that the fluid is coming in uniform velocity. The if at all there are any surfaces, they are too far away for any velocity variation of the fluid. It is coming in uniform velocity and it is entering this region between two parallel plates. And from your fluid mechanics course you are familiar that, and also from your school you are familiar that, school level or introductory college level physics, you are familiar that the velocity profile that will ultimately develop is a parabolic velocity profile that is shown in these pictures. Now so the fluid enters the region between the parallel plates from a region that is much wider. From a microscopic or continuum perspective, the fluid may be visualized to comprise a number of infinitesimal quote-unquote fluid particles. In each fluid particle, I can still model the fluid from a Now, if I were to look at an arbitrary infinitesimal fluid particle, and I am going to depict it as a cube, all right, this particle is alongside many such particles, and this particle is in the region before the two parallel plates start. So it is in the region of, width h, which is much greater than 2b, right? Now let us consider this particle. The velocity of the particle, let us assume to be v, and it could have in principle three coordinates, three components, because velocity is a vector. There is a magnitude for this velocity which we call as speed, and then there is a direction. So there is a vx, there is a vy, there is a vz. This is a vector, and the driving force for this flow is external. There probably is some high pressure region where the fluid is pressurized to flow in a certain direction, and that force is external driving force. Let us call it as F. And again, since that force has a magnitude and a direction, now it will have three components: Fx, Fy, and Fz. Now, if I were to consider the cross-sectional area of the x-plane as ax, that is the yz planes, y-plane or the zx plane to be ay, and the z plane or the xy plane, if the cross-sectional area are az, then I can define pressures. Px is equal to Fx by Ax, and Py is equal to Fy by Ay, Pz is equal to Fz by Az, and that will result in the pressure, basically the quote unquote normal pressures that is exerted. There is an x component pressure, there is a y component pressure, there is a z component pressure, and so on and so forth. Now, why is this called normal pressure? Because this is parallel to the normal vector for that particular cross-sectional surface, the plane x plane, y plane, and z plane. Now let us further consider how the fluid flows is before the region between the two parallel plates. This external force that I am talking about is a contact force. As I was mentioning, it could be by some pumping of the fluid or pushing of the fluid by a moving surface or whatever it is which drives or causes the fluid flow. There may also be body forces involved, such as gravitational forces. There are also electromagnetic forces which can cause flow. They are defined by what are called fields, which cause motion without physical contact, and these body forces are not expressed as pressures. Per Newton's first law of motion, the parallel plates are not yet encountered. So once this pressure is exerted, this motion should be the motion that is set in the fluid particle is set into the motion that is characterized by the velocity v, and the pressure p, right? This motion should be the new inertial state. Now the fluid should continue to exist in this state of uniform motion defined by the velocity v, unless another external force acts on it. Now, upon entering the region between the two parallel plates, a second external force comes into play. This external force is the friction between the plate's surface and the fluid. This is the frictional force or a shear force. Now what will happen? A stationary surface will retard the flow of the fluid particle that is in contact with that surface, right? So if the purple molecules, essentially purple colored system, is basically the surface, stationary surface, then the first green colored molecules that are there right above the purple colored surface would be the so to speak. And of course keep in mind that we should be careful not to confuse molecular length scales with continuum length scales. So really, when I'm talking about the fluid particle that is in contact with it, it's not a single molecule. It is a large collection of molecules. Recall once again, for this continuum behavior to be valid, Knudsen number should be at least less than 0.01, and therefore there are a large number of molecules in that fluid particles. So now we should probably look at this same picture. Instead of looking at them as individual molecules, you should probably look at them as individual fluid particles. Now if the first green level fluid particles that are right above the purple surface, right, if the green fluid particles, if they are in contact with the surface, since the surface is stationary, it will retard the flow of the fluid particle that is in contact with it. Now it will be this. How does this happen from a molecular perspective? This fluid particle in contact with the stationary surface will be held back by what are called wetting forces or adhesive forces. And if these adhesive forces are strong enough, then the fluid particle will not slip past the surface, will not slide past the surface. Such a condition is often called no slip condition, and for the no slip condition, we typically assign the velocity at the boundary to be 0. And if since both these parallel plates that we are looking at in this problem are stationary at y equal to plus b, one plate is located at y equal to minus b, the other plate is located at both those plates, the velocity of the fluid should be 0. Now, since the fluid flow is largely in the is at the time of entrance is entirely in the x direction, that x momentum that these fluid particles that come together form a single layer of fluid that is in contact with the surface y equal to plus b, and another set of fluid particles that together form a layer of fluid that is in contact with the surface denoted by y is equal to minus b. All those fluid particles, they will be, their x momentum will be arrested, they will be taken by the surface, and therefore their velocities, x velocities at that those y equal to plus b and minus b, they will become 0. This is the no slip condition. So the stationary particle wetting the surface. Now we are looking at the first layer, that green layer of fluid particles that are now wetting the surface, and they are retarded, they are not moving at all, they are stopped. Those particles, that layer will further retard the flow of the particle below it. If you are looking at y is equal to plus b, then it will retard the flow of the particles, fluid particles below it. If you are looking at y equal to minus b, it will retard the flow of the particle above it. So between minus b and plus b, in other words between the two parallel plates, each layer of fluid particle will be further retarded. The x momentum will be further reduced and reduced. However, what happens is, due to its ability to deform. What do I mean by deform? In a fluid, secondary bonds are more easily broken and reformed than in a solid. And therefore, now the secondary bonds are weaker, and therefore the second fluid particle will be able to slip past the stationary fluid particle. So the fluid particles at all at a specific y in a single layer or lamina will therefore typically all be retarded in a uniform manner in this model, that in this picture that we are creating, and therefore will all typically flow at a certain velocity in the x direction. So at y equal to plus b and y equal to minus b, this velocity is 0. Then the next layer of fluid particles, there will be a non-zero velocity, but it will be very, very small. And then the next layer of velocity, the fluid particles, the velocity will be slightly larger, and on and on and on, coming from both sides till you reach the center. So what is happening to this x momentum that has been arrested, that has been removed? Where is this x momentum going? This x momentum is transported in the y direction. You have to remember that what happened to all that x momentum of all the fluid particles that formed the first layer, that is wetting and in contact with the surface, either y equal to plus b or y equal to minus b. All of that momentum went where? It went into the solid. The solid arrested all that momentum. It took all that momentum, right? And it dissipates that momentum by way of vibrations of the solid, the molecules that comprise the solid. But of course, those solid molecules are not going to move unless there is a tremendous amount of momentum that is transported to that solid, right? There is this recent There is this recent rumors or facts, we don't know, some statements that are being made to the fact that there is a dam in China called the Three Gorges Dam that is giving way. Essentially, what does this mean? There is a huge amount of fluid that is coming and impacting that solid surface, and what should have been a stationary fluid that is wetting that surface is now able to exert so much momentum, and the rate at which this momentum is changing, which is the force, that force that is being exerted on that dam's walls, the surface, is so large that that solid is breaking, and therefore the dam gives way and there is a flood, right? So unless such very large quantities of momentum are gets transported in the y direction to the solid surfaces, the solid surface will absorb all the momentum that it picks up, and it will remain stationary. Therefore, the x momentum that is picked up, that is removed by way of friction, is transported in the y direction to the solid surface. The solid surface remains stationary, and subsequent to it, each and every layer of fluid has slightly more and more and more momentum available to it. So what is happening is that x momentum is transported in the y direction, and this happens because of quote unquote molecular collisions, intermolecular interactions, which are captured by these kind of secondary bonds that are broken and reformed. Now, in other words, the x velocity now of a fluid particle depends on the y position that fluid particle is at. Remember, before entering the region between the two parallel plates, everywhere there was a uniform x velocity, just one constant v. But the moment the fluid enters the region between the two parallel plates, now a velocity profile develops with zero velocity at both surfaces and maximum velocity at the center. And therefore, Vx, the velocity of the fluid along the x direction, is a function of where that fluid particle is present along the y direction. Is it at a fluid layer which is wetting the surface? Then Vx is 0. Is it at the fluid layer that is at the center, in other words at y equal to 0, then Vx is maximum. Is it at a fluid layer that is wetting the bottom surface, which is y equal to minus b, then again the xvx velocity is 0. So fluid essentially flows in y planes or layers or laminae of constant velocity, hence this term laminar flow. So therefore, the velocity increases gradually from Vx is equal to 0 at a surface, at a stationary surface, until a maximum is established far from the stationary surface. And this is at y is equal to 0, or the center between the two parallel plates. This velocity, the maximum velocity, is the same as the one the fluid had before entering the region. In other words, you could argue that the central layer of fluid is the one that has experienced practically no friction. This means the momentum along the x direction is lost in the y direction, eventually into the stationary plate, which absorbs it and dissipates it as vibrations of the solid atoms in the plane. And this is your frictional force. So fundamentally, if you look at what is the difference between friction in solids and friction in fluids, basically what happens is, in both cases, it is the stationary surface that absorbs this momentum, and that momentum is dissipated as vibrations of the solid atoms that are present, the atoms of the stationary surface. All right, and that part doesn't change. But when it comes to a solid, which is undergoing a flow, or in this case motion, right? Solid undergoing motion, then we since the bonds between all the various quote unquote layers, if you were to consider equivalent layers of molecules, particles in the solid, if you were to look at it, they have much stronger bonds. The cohesive forces of the solid trumps over the adhesive forces, or the wetting forces between the solid and the surface. and therefore there is friction, but that is confined to the interface between the solid stationary surface and the moving rigid body, solid body, right? It is confined to that, those two individual layers, or maybe a few layers at best. There is no thought, there is no consideration that there could be a velocity profile of the various molecules in the solid. This would mean that the solid would deform, right? So one layer of molecules is moving at a certain velocity, another layer of molecules is moving at a different velocity. This is the classic case of something like a rubber elastically stretching, so to speak, right? So the edges move at a much greater velocity than the center. For example, if you take a rubber band and sort of stretch it out, or a balloon and sort of stretch it out, right? So that would be the way of thinking of a solid, but that doesn't happen. I mean, we assign a single velocity to the entire rigid body, and then we say, hey, you know what, there is a frictional force and a certain amount of momentum is lost. Whereas when it comes to fluids, because the cohesive secondary bonding between the fluid planes or laminae are possibly weaker than the wetting or adhesive forces between fluid and a solid surface. If such a situation exists, then there will be no slip at the wall, and that means the velocity of that particular layer of fluid at the surface becomes zero. This basically means that you have a velocity profile. Like this, you have the next layer with a slightly higher velocity, and so on and so forth. Now you have essentially flow instead of motion, mere motion, right? And you have a velocity profile. In either case, the momentum along one direction is lost in the other direction, perpendicular direction, right? Now, I hope you realize that force is the rate of transport of momentum. We have emphasized this in previous lectures, and this has been taught in schools as well. Time rate of change of momentum is force. Therefore, frictional force in this problem is a measure of the rate at which x momentum is transported in the y direction. That is an important understanding to gain. So, in other words, this frictional force, which as I just said, is the rate of transport of x momentum in the y direction, that force acts tangential or perpendicular to the direction of flow. It is also called a drag force because fluid particles in one plane, which is any plane parallel to the direction of flow, are effectively either dragged behind or dragged ahead by the fluid particles in adjacent planes. Once again, to sort of reiterate, this basically means the momentum along x direction is lost in the y direction, eventually into the stationary plate. Thus, frictional forces in a fluid are characterized by two directions. This is the take-home message that I would like you to have. To characterize frictional force in a fluid, it is not enough to have one direction. You need two directions. And this is something fundamentally new in terms of a mathematical requirement. You are familiar with quantities that are scalars that have just magnitudes associated with them, but no directions. For example, density or specific heat or viscosity or these kind of various properties that you know, concentration, right? These are all basically scalar quantities. And then you are familiar with quantities to which there is one magnitude and there is one direction associated. So that is associated with when something has some direction of flow, for example. So there is a velocity with a vector, there is a direction in which a force acts, so there is some sort of a direction in which that force is acting on another object, right? So there is a magnitude, there is a direction. You are familiar with vectors, but now we are encountering probably for the first time in an explicit manner forces which are characterized not by one directions but by two directions. One is the direction of flow and the other is the perpendicular direction of loss of momentum. So the x momentum, which is the momentum associated with the direction of flow, is lost in the y direction, in the perpendicular y direction. Thus, as I mentioned, the shear or frictional force acting on a fluid element is now characterized by two directions. One direction is the direction of flow itself, and that is in the x direction, and the other is the direction of loss of momentum to a surface which is present at some distance in the y direction away from this fluid particle. So there is one stationary surface present at y is equal to plus b, and then there is another stationary surface that is present at y is equal to minus b. So therefore there are two surfaces that are present to which the momentum is being lost, right? So therefore, to describe this shear or frictional force acting on a fluid element, now you need to indicate F with two subscripts. One subscript indicating the shear force, and therefore the first subscript indicates the direction in which this shear force itself acts, that is the y direction. That is the direction of the momentum being transported. The momentum is transported in the y direction towards the surface by this molecular momentum transport mechanism, right? Now the other subscript that you have to say is, where did this momentum come from? This momentum came from the x momentum of the fluid, and therefore the second subscript x indicates the direction of motion of the fluid. So the shear force or frictional force of this fluid element is indicated by F with a subscript of yx. To reiterate, the shear force is the rate of transport of x momentum in y direction. Understand that rate of change of momentum is force. Therefore it is the rate of transport of momentum, and now we are looking at rate of transport of x momentum in the y direction. The corresponding shear stress, which is the force per unit area, is given by tau yx is equal to fyx by the area. What is this area? This area is the area of contact through which this momentum is being transported, and that is basically given by L, which is the length of the two parallel plates, and W, which is the large width that is there. Infinitely large, well, not exactly infinitely, in the sense that it is much larger than the distance between the two parallel plates, right? So LW is the area. The extent of reduction of Vx along y direction is clearly proportional to the shear stress. In other words, there is a gradient of, or there is a change of the Vx, the x momentum along the y direction, and this is basically because the remaining x momentum, the momentum that is reduced, so to speak, is transported along the y direction eventually to the surface, the stationary surface, which absorbs that momentum and dissipates it, right? Therefore the the shear stress, which is the force per unit area. Now what is force? Again, you understand it is rate of transport of momentum. So force per unit area is rate of transport of momentum per unit area. That is flux of transport of momentum. So this is the shear or frictional or molecular momentum flux, right? That is the shear stress. Tau yx is, to reiterate, molecular momentum flux in the y direction of the x momentum that was available to the fluid when it was coming into the region between the two parallel plates, and therefore the extent of reduction of that x momentum is clearly proportional to the shear stress, right? And therefore there is the simple law that is attributed to Newton called the Newton's law of viscosity that captures this proportionality. Tau yx being the shear stress, which is the flux of x momentum transported in y direction to the surfaces, and the dvx dy being the velocity gradient of the fluid along the y direction, right? That the change rate of change of velocity in the y direction. This relationship need not be linear, but there are many fluids that do exhibit this linear relationship between the shear stress and the tangential velocity gradient, and such fluids are called Newtonian fluids. And the proportionality constant mu for this linear relationship is called viscosity. Now, to summarize momentum transport due to friction in laminar flow. This is the molecular momentum transport. The molecular momentum transport occurs in such a fashion that momentum gets transported from a region of high momentum to a region of low momentum. On the other hand, the momentum transport due to bulk flow or pressure driven flow it happens in such a manner that momentum is transported from a region of high pressure to a region of low pressure. Look at it once again. The entrance to the region between the two parallel plates, that is the region of high pressure. The exit from the region between the two parallel plates, that is the region of lower pressure. Similarly, when we are looking at molecular momentum transport, the central plane or lamina of the fluid has the highest momentum, and on both sides, as you go towards the stationary surfaces, the momentum is lower, and therefore this molecular momentum transport happens from a region of high momentum to a region of low momentum. The idea being it retards the flow. The pressure difference, which is basically the driving force for the bulk momentum transport, this is necessary to maintain a steady flow because there is a steady loss of momentum due to the molecular momentum transport. And therefore, if the pressure difference is not sustained, then the flow will eventually cease. Eventually, the fluid will move to a stop. And this is something that we see actually happening. If you take a glass of water and pour it on a floor, on a surface, initially the fluid has some momentum, so it will spread across the surface. But eventually the fluid does not have any sustained initial force that was given, right? And there is no sustenance of that force. So eventually all the friction will ensure that the fluid spreads into some sort of a puddle, but it is a stationary puddle. So this brings us to the end of this lecture. This lecture is designed to introduce to you how molecular momentum transport happens. What are the key features of molecular momentum transport? And what is this parameter called viscosity? I hope you've been able to follow, understand, and I hope you're able to answer these questions now. This is not a very simple lecture. There are some involved concepts involved. So I hope if you need to listen to this lecture again, please do so. If there are any questions, please feel free to contact me. You can either post them as always in the comment section, or you can contact me and I will clarify the questions that you may have. So thank you for listening to this lecture and you have a wonderful day.